Hello everyone. Today I wish to discuss the question, how well can multiple parameters be estimated simultaneously? This talk is based on a paper we have recently put on the archive titled Efficient Computation of the Nagioka-Hayashi Bound for Multiparameter Estimation with Separable Measurements. The main result of our paper is that we have shown that the maximum achievable precision in quantum metrology when we are restricted to separable measurements can be computed in an efficient manner. In this talk, I'm going to introduce quantum metrology, and in particular separable measurements, and then I shall discuss our main results. Hopefully, by the end of this talk, I will have convinced some of you of the importance of separable measurements, and by extension, our results. I will begin with an outline of our results. Our main result is that we present a new bound for parameter estimation, which we call the Nagioka-Hayashi bound. This bound is powerful for two main reasons. It is valid for separable measurements on a finite number of copies on the probe state. This is in contrast to the more commonly used Holevo bound, which in general can only be reached with a complex collective measurement on infinitely many copies of the probe state. For this reason, the Nagioka-Hayashi bound is in general tighter than the Holevo bound. The bound is named as such after two important papers. The original bound was introduced by Nagioka in 1989 for the estimation of two parameters. For the case of estimating physical observables, Hayashi extended the original Nagioka bound to more than two parameters. In this setting, the minimization problem is different to that of the parameter estimation setting which is shown. Our contribution is to write down the generalized Nagioka bound for parameter estimation problems based on Hayashi's method. We have further shown that this bound can be computed efficiently, making it easily accessible. Finally, we have illustrated the importance of this bound with two physically motivated examples. The first thing we need to know is what is quantum metrology and why is it useful. Quantum metrology is using quantum mechanical resources such as squeezing and entanglement to measure some physical quantity more precisely than what is possible classically. One example where quantum metrology has had huge success is in the detection of gravitational waves. Since the injection of squeezed light into LIGO, the number of gravitational wave detection events has increased dramatically. This is a really fundamental example of where quantum metrology is useful. Another example of a quantum-enhanced measurement is in the simultaneous estimation of optical phase and loss in an interferometer. In this example, carefully tailored entangled quantum probes were shown to maximize the measurement precision which can be achieved. So there's a lot of optimism surrounding quantum metrology and motivation for further studies. I will now introduce the basic notation that we will be using throughout the talk. We have n parameters of interest, denoted here by the different thetas. These theta describe the quantum state and may represent physical quantities we wish to learn about. These quantities are encoded on the density matrix of the system. This generally happens in one of two ways. Either we wish to learn something about the quantum state itself, or the quantum state passes through some channel and the parameters are encoded onto the density matrix. In order to learn about these parameters, we then measure the quantum state. The most general measurement in quantum mechanics is a positive operator valued measure, or POVM, denoted here by pi k. There are some conditions these POVMs need to satisfy in order to be a physically meaningful measurement. Namely, they are required to be positive matrices and they must sum to the identity. Based on the different measurement outcomes that are obtained, an estimate of theta is produced through some unbiased estimator. With sufficiently many samples, the estimated parameters should converge to the true values. We quantify how well a particular measurement and estimator performs through the mean square error matrix, denoted here as V. The theta hat values are our estimates of the true values theta, and p theta of x is the probability of the measurement outcome x. This is a measure of how far the predicted theta values are from the true values. Quantum metrology aims to optimize our measurement choice in such a way as to minimize the trace of the mean square error matrix. It is natural then to ask, just how good can a measurement be? Although I have described some situations where quantum resources benefit measurement precision, in some respects quantum mechanics can actually be detrimental to measurement precision. For example, the uncertainty principle implies that we cannot measure any number of quantities with an arbitrary precision. The ultimate limit on how well a set of parameters can be measured was introduced by Holevo and has since become known as the Holevo bound. It is computed through the minimization problem shown. A similar bound was introduced by Nagaoka and is referred to as the Nagaoka bound. In this form shown here, the Nagaoka bound is applicable only to estimating two parameters. Both of these bounds have been known for a long time, however they have remained somewhat elusive owing to the difficulty in computing the optimal X matrices. We now add a new bound to this list, the Nagaoka-Hayashi bound, which generalizes the Nagaoka bound to estimating more than two parameters. As this bound can be computed efficiently, it should be easily accessible. All of these bounds involve an optimization over the Hermitian matrices Xi, which are subject to unbiased conditions. We will now look at the difference between these two bounds. In his paper, Nagaoka introduced another bound which he called the most informative bound, denoted here as CMI. This was defined as the minimum variance which can be achieved by any POVM and unbiased estimator. In general, this bound is a tighter bound than the Nagaoka bound, which is in turn tighter than the Holevo bound. The Nagaoka bound and Nagaoka-Hayashi bound apply when we restrict ourselves to separable measurements. In contrast, to reach the Holevo bound, we require a collective measurement in general. In some specific cases this is not true, and the measurement strategy required to reach the Holevo bound is known, for example, for estimating two displacement parameters of a Gaussian state. In this example, the measurement which reaches the Holevo bound is a separable measurement, and collective measurements aren't necessary. But in general, a much more complex and experimentally challenging measurement is required to reach the Holevo bound. A separable measurement means we can measure our probe states individually, so we prepare and measure our probe states one by one. With a collective measurement, we are required to measure all of our probe states simultaneously. If we are receiving the probe states one by one, this means we need to be able to store the quantum probes until all have been received, and then we can measure them all simultaneously. Obviously, this is considerably more experimentally challenging than a separable measurement. In addition to requiring a complex collective measurement, the Holevo bound is in general only asymptotically attainable. This is the main motivation for our work. The Nagaoka-Hayashi bound, being a bound on separable measurement precisions, represents an experimentally feasible bound. This brings us to our main results. Without going into too much detail, we write the variance from the optimal POVM and estimator as V star. This is the best possible measurement precision when restricted to separable measurements. We write V star in terms of S theta and L star theta. S theta is an extension of the quantum density matrix of the probe state in an extended classical quantum Hilbert space. L theta is a set of operators on the same extended Hilbert space made up of the tensor product of the classical matrix of error elements with different POVMs. For convenience, I have shown L theta here for the estimation of three parameters. L star theta is the optimal L theta which minimizes the total variance. With this notation, we can write the Nagaoka-Hayashi bound as shown as a minimization over the matrices L and X. This is a new bound for multiparameter estimation with separable measurements. We have further shown that this computation can be recast as a semi-definite program meaning the minimization problem involved in this bound can be computed in an efficient manner. Prior to this, when computing separable measurement precision, the most common approach was to try and explicitly find the optimal measurement strategy, i.e. find the best POVMs and estimator. However, as the dimensions of the system in question grows, this becomes computationally expensive very quickly. Our program offers a method to circumvent this. I will also point out that a similar result was obtained recently for the Holevo bound. We hope that the ability to efficiently compare the precisions attainable with both collective and separable measurements will be very useful to the community. I will now illustrate the importance of our results with two physically motivated examples. Our first example is the problem of trying to estimate 3 rotations about the x, y and z axes of the block sphere using a 2-qubit probe. Our input state is the maximally entangled 2-qubit state. 1 qubit in the probe experiences the different rotations and is then subject to the phase damping channel. The effect of the phase damping channel is to shrink the block vector along the x and y axes. The second qubit experiences only the identity channel. In this figure, we show the Holevo and Nagioka-Hayashi bounds for simultaneously estimating these rotations. The superscript number in the legend indicates how many rotations we are estimating simultaneously. The Holevo bounds are represented as solid lines, and the Nagioka-Hayashi bounds are represented as dashed lines. For estimating a single parameter, it is known that collective measurements offer no advantage, and so unsurprisingly for this case, we found that the Holevo bound coincides with the Nagioka-Hayashi bound. However, for estimating 2 or 3 parameters, the bounds are different. However, for the 3-parameter case, we see that although separable measurements are inferior to collective measurements, the gap between the two is quite small. This suggests that it may not be worth searching for the optimal collective measurement strategy, as the benefit from the potentially complex collective measurement required is not that large. Our second example concerns the simultaneous estimation of phase and loss in an interferometer. We consider the most general photonic input states of the form shown, which have a maximum of n photons. For all n up to and including 14, we found that the Holevo and Nagioka-Hayashi bounds coincide. We were actually able to show that there always exists a POVM which reaches the Holevo bound. This implies that for this particular example, collective measurements offer no advantage. This is another demonstration of the power of the Nagioka-Hayashi bound. Rather than searching for some complex collective measurement to saturate the Holevo bound, if we know the two bounds coincide, we can focus instead on searching for a separable measurement which will reach the Holevo bound. I will leave you with two very interesting possible avenues for future work. The most obvious question to come out of our work is whether or not the Nagioka-Hayashi bound is always attainable, i.e., can we always find a separable measurement scheme which reaches the Nagioka-Hayashi bound? In the two examples that we have considered, we have found this to be true, but it is not necessarily true from the way the bound is constructed. This is something we are currently investigating numerically. However, in the cases where we can find a counterexample to this claim, it is difficult to say if this is because the claim is not true, or if it is because of some deficiency in our numerical POVM search. The second question concerns the attainability of the Holevo bound. In general, we know that a collective measurement on infinitely many copies of the probe state is required to reach the Holevo bound. The Nagioka-Hayashi bound allows us to investigate this. By looking at the separable measurement precision on multiple copies of the probe state, we have a way to investigate just how difficult it will be in general to reach the Holevo bound. This is something we have been working on and will hopefully share with everyone soon. Finally, I would like to finish by thanking those without whom this work would not have been possible. I would like to thank Jun Suzuki from the University of Electrocommunications in Tokyo, and my own two supervisors here at the Australian National University, Ping Koi Lam and Saeed Assad. Thank you all for your attention, and I hope you enjoyed the talk.